Hey guys, so this week we're talking about experiment 4, fractional distillation as opposed to steam distillation or simple distillation. So the difference between steam distillation, simple distillation, and fractional distillation isn't that different, but they are extremely important when you consider the differences. Now, the real strange differences are with steam distillation, you're trying to isolate one product and you're using water as the mobile phase, the organic phase, your solvent phase. Water, even though it's not organic, it's aqueous. As we know, just to reiterate, the steam distillation process just heats a compound up and it carries it with the steam into the vector, the machine that you would like to analyze it with. Now, simple distillation is for separating compounds with boiling points that differ greater than 40 degrees Celsius. And fractional distillation is for compounds that differ in boiling points that are less than 40 degrees Celsius. So for instance, when we were trying to differ our N-hexane and our toluene, difference of boiling point 41-ish degrees Celsius, we would use simple distillation. In fact, we would just boil to 1 milliliter of each compound combined together, boil them off into Hickman Hill stillheads, take one fraction of each, including a second fraction, which is combined, ignore the second combined fraction, and only analyze the refractive index of our 1 and 2 fractions. So now I'm going to share my screen with you and go through each of the questions you guys have. I believe you guys have the screen now. So I'm going to quickly go through some of the questions you might have. So question 1, I'm literally going to go through the questions like this because I want to make sure that you will understand what's happening and you put down correct answers. The only way to put down correct answers is to, unfortunately, I'm sorry, listen to my boring freaking lecture. So I'll make this as concise as I possibly can. Question 1, ladies and gentlemen. So the difference between steam, simple, and fractional distillation. Well, we know that now, right? Because steam distillation is the process of heating up a compound and using the steam to carry that one compound, one singular compound, to the point at which you can measure it, then removing the water and then measuring how much of that compound you resulted in. Now, we have something like simple distillation, which is a difference of greater than 40, which we've already seen, where we can separate our toluene versus our N-hexane, all right? Then we have something more like fractional distillation, whereas we use the spiral column magnetic stirrer to fractionally separate different solvents of boiling point temperatures with less of a difference than 40 degrees Celsius. So a common physics joke about the same exact stir bar is an inverted plane spiraling a vertical axle. What do we get? We get screwed. That's the joke. The punchline was ill-delivered, but the initiation was ill-delivered, but the punchline is we're screwed. In this case, however, a screw is exactly what we need, because for fractional distillation, each inverted plane on each incline on the axis. So as you see the inverted plane of the magnetic stir bar, my finger being the long rod, and my other finger here being the wrapped around inverted upward plane, which creates the screw, aka the Archimedes screw. Fun fact, the screw itself was invented by Archimedes, which I'm sure you've heard of, in his bathtub, when the emperor of Rome at the time asked him to determine whether or not a crown was made of genuine gold or not. Now, we know that different substances have different densities, meaning that they contain different volumes. So even though the crown was an irregular shape, meaning it couldn't be measured using mathematics and algorithms, he was able to dip it into a pool of water, Archimedes was, able to dip the crown, the golden crown, into a pool of water and see how much water it displaced. So let's pretend that this irregular golden crown displaced 10 meters of water, or was supposed to displace 10 meters of water if it was pure gold. Now, the emperor of Rome at the time wanted to find out whether or not it was a real purely golden crown, or whether or not he was being screwed over by the commoners. So he hired Archimedes. Archimedes decided during his bath that he'd be able to determine the density of said crown by putting it into water and seeing if it equaled the density of gold at that time, which it did not. So the people who actually made the crown were executed, and Archimedes was eternally memorialized in this moment. Kind of sad, but also a memorable moment for all of us scientists. Just to point out, something for you guys to remember. But for this question, the difference between simple steam, or steam, simple, and fractional distillation. Steam is to isolate one compound. Simple is to isolate two of difference of boiling point of greater than 40 degrees Celsius. And fractional is to separate more than two of less than boiling point difference, 40 degrees Celsius. Meaning that the turning spin vane, aka the spinning screw with the inverted plane, on each inverted plane axis has its own different gas vapor pressure equilibrium. Okay, so we know about equilibrium, and we know at a certain standard temperature and pressure, equilibrium follows through. So if you're heating the bottom of this system and the top of the system is not heated, all right, and it's a prematurely mostly closed system, meaning the top of it is only obscurely closed, then we are able to quantize the volumetric spatial areas of the reaction based on the energy that they're releasing, okay? And this is the most important part of this lecture video, is the quantization, because if you have a screw that's going up, we know that it gradually rises in a circular motion. However, in a horizontal state rhyming motion, now let's just pretend that each of the climbing rises to the next level in this horizontal or vertical inverted axis represents its own standard temperature and pressure at which solvents interact, vaporize, can be detected, etc. So what we do is we heat up these boiling points. And because we have a screw, an inverted vertical axle with an inverted plane wrapped around it, each one of these levels of height has its own standard temperature and pressure, even though it's extremely minimally different, that which it vaporizes and can be detected at. So I know I've been talking and rambling a lot for quite a bit, but now, if you've stuck along quite along till now, I will start to dive through these questions. Difference between steam, simple, and fractional distillation. Steam is isolating one product. Simple is isolating two products, which differ by a boiling point of 40 degrees Celsius or larger. Fractional is separating more than two products of boiling point less than 40 degrees Celsius. All right. So for the really fine, nitpicky stuff, briefly describe in your own words the overall idea of refractometry and refractive index. So I pulled up a little diagram for you guys to follow along for this, and I will bring it up right now whenever I can. And the difference between and why refractometry is extremely important to us is very important. I want to go over it very briefly. So there's a very big difference between dispersion, diffraction, and refraction. And I hope you guys can see my screen right now. Diffraction is when you send certain beams to a point and they start to bend, all right, with the medium that they travel through. Refraction is similar, but to the point where the wavelength differs but doesn't continue to differ after it hits that point. Dispersion is when you take a singular wavelength and you disperse all the individual wavelengths that are composed into that one. Because when you see a certain beam of light, it doesn't always necessarily mean that that is the individual wavelength of that light. When you see a certain beam of light, that means that is most likely in almost every circumstance that you will visibly be able to measure is a measurement of combined wavelengths. okay? So a lot of white light that we see is a combined ratio of different wavelengths, red, blue, and green, that we can combine into what we observe and talk about today. Now, there's another question about the short answer for the IR, about the hexane, toluene, cyclohexane, and 2-methylpentane. Now, I have examples of each of these up here. So here you see cyclohexane. I am demonstrating. I hope you guys can still see. And around 3,000, we have extreme peaks showing up with this minor peak here and this very extreme dip. I know it's hard to see, which is why I'm alliterating it on the SciFinder website. And then moving on, I know it's not in order, but I put it to you in this exact order for a reason. Cyclohexane. So now we're moving from a cyclo organic compound to an N organic compound, a normal organic compound. And now we see a very similar peak. However, the secondary peak is much closer to the residual peak that we're observing. Just something to note and something to definitely put in your report that I will grade you upon. And then here even further. So now we have the same technical compound, 6 carbon atoms, but instead of it being in a cyclohexane organization or an N-hexane organization, we have 2-methylpentane. So we have 6 carbon atoms arranging themselves in a figure that arranges a pentane figure. And we have an even less figure here. And I know that they switched at one point, meaning you used to see peaks facing upwards, pointing in this direction, and now you see peaks pointing in this direction. I would like to point out that between these two graphs, which I am consistently switching between, they are the same. We see 3,000 here if you follow my mouse, and we see 3,000 here if you follow my mouse. The difference is this tiny little peak here and this tiny little peak here, which show the smaller peak residual next to how normal it is. Now, that is something definitely to reference in your reports. Now, moving on, we have 2-methylpentane. Now we see the same exact result up to 3,000 switched, inverted on the y-axis, switched to face downwards. So now we see this 3,000 point axis on the wave number axis with this lesser peak coming even further up the peak of the 3,000 point. Now if we move even further along, we see this toluene. Now the big difference between toluene, your 2-methylpentane, and your cyclohexane, your N-hexane, is that you now have an aromatic compound. So you now have a compound that follows Huckel's rule, the N2 plus 4 rule. So that is a very quick and easy and dirty way to identify toluene. And now using just these analytical depictions of what your spectra should look like based upon these compounds, it should make it extraordinarily easier to elaborate which compounds you are analyzing when you observe spectra in our lab. Even though these will not be exact, they are, again, just reiterations based upon several dozens of hundreds of thousands of algorithms, but they are not exact. I will reiterate that. Moving on to the next question, so I can help you guys out. You were able to collect 2 fractional and obtain gas chromatography from your lab instructor. Yes, you were. So I gave you guys the refractive index of both the toluene and the N-hexane, okay, but not the cyclohexane and the 2-methylpentane. So the gas chromatograph results of the cyclohexane and the 2-methylpentane will be included in the description of this video or in an email I'm about to send you. But the point of refractometry, which I would like to elicit for a previous question and also help you with this one, is that every single compound, every single one, especially the ones you'll see in this lab, let's just include liquid compounds. And when I say liquid compounds, I mean liquid at standard temperature and pressure, meaning at any earthly regular standard temperature and pressure, they are liquid. So they all have different refractive indices, meaning that when plain polarized light hits this media, my fist being the media, it bends or turns or refracts at a certain degree, okay? And as it does so, very, very fine-tuned machines that we have that are equipped can measure this difference in angle, all right? Not the, so what it does is it measures the angle of entrance and the angle of exit. And it takes the ratio of those angles, and that's where you get your refractive index. So every single compound has its own extremely unique refractive index. And this is what we use to determine present compositions of compounds that we're trying to distill or isolate from one another. So which is why we use the gas chromatograph to isolate cyclohexane and 2-methylpentane. Because we know that cyclohexane and 2-methylpentane, although their boiling points differ by less than 40 degrees Celsius, about 18 degrees Celsius to be exact, they can be separated because if we use a fractionating column, meaning one of those spiral columns, each one of those inverted planes moving up the vertical column has a different standard pressure and temperature. Even though it's extremely slight, it does have a significant difference in standard temperature and pressure in which it can measure and accurately differentiate two different solvents with two different boiling points less than 40 degrees Celsius. Not less than, let's say, like half a degree Celsius, but less than 40 degrees Celsius, spot on, definitely. So that, I hope, answers your question for number 5. The fractional distillation question, cyclohexane and 2-methylpentane. You're able to collect 2 of them, and here is your lab instructor data. I would like you to use the peak height and the peak width at half height from the video because, and this is strictly because, the calculations and identification of the chemistry involved can only be interpreted if you accurately watch and understand the video. If you have trouble with the video, that's where my office hours that I've been doing will come in handy. Otherwise, you're gonna have a lot of trouble. I'll be able to pick up on it, and it will give me an opportunity to re-record this video or send you another. Moving on, briefly describing your own words, the overall idea of gas chromatography. All right, gas chromatography, if I can elicit you in a very brief circumstance, you are trying to separate cyclohexane from 2-methylpentane, all right? They have different boiling points of 18 degrees Celsius. So you inject your sample, all right? It's a mixed sample of 2-methylpentane and cyclohexane, completely mixed. Now, their boiling points differ from 18 degrees Celsius. So as we heat up the medium, the column, we are going to see a dispersion of the 2 compounds. And this is because we have a carrier gas, all right, stationary, and a mobile phase. In all chromatography, all of it will have a carrier phase and will have a mobile phase. In this circumstance, your mobile phase is nitrogen, some inert carrier gas like nitrogen or radon, etc. And then radon's more expensive, so we use nitrogen. And then your stationary phase will just be regular atmosphere. So when you insert your cyclohexane to your 2-methylpentane, one of them has a lesser boiling point of about 18 degrees Celsius difference, and that one is going to speed up more. Its individual molecules will increase in energy as the column begins to increase in temperature. All right, because what do we know about increase in temperature? Increase in temperature, if my little cornucopia here is a molecule, we increase the temperature, we increase the energy, all right? So we know it's moving around, because when you boil water, what happens? The molecules bump around and move frantically and crazily. So as you increase the temperature of this column with the solution of 2 cyclohexane solution combined in there, each one has a difference in boiling point of 18 degrees. So each one is going to vibrate, all right, gain kinetic energy from the potential energy of temperature by a certain degree, all right? And because their boiling points differ by 18 degrees Celsius, the degree to which they absorb this energy is going to differ greatly, all right? So even though they have a boiling point of only differing less than 18 degrees Celsius, because we heat up the system, we're able to differentiate them further based upon their boiling points. Understand? All righty. Okay, we're making some progress. So, which boiling point would you expect to come out first? And I will leave that one up to you. And I'm sure I'm going to get a lot of emails asking this question and asking you to explain it more. But it's an extremely easy question. I would expect most of you to guess on your first response. And I would expect the majority of most of you that guessed to get it right. It's a pretty easy response, pretty easy guess, and pretty easy intuition as to what energy state a molecule might enter going along the gas chromatography, knowing that the temperature is increasing as it goes through the gas chromatography. So I give you guys a lot of answers, very straightforward through these videos, but that one I will leave up to you. The following one, I have a video prepared actually, and that's for balancing chemical equations. And first off, I will say this is a very simple, regular balancing equation. You guys have all the time in the world to try and figure it out. You are just trying to make sure that the balancing of the atoms, the carbon, oxygen, and hydrogen work on both sides. I will tell you that balancing the carbon and then following balancing the hydrogen and then following balancing the oxygen will work best. But let's listen to the experts. Carbon. Now, I will assure you that these answers are correct, aside from maybe some slight simplification. But essentially, all you have to do is balance the carbon, then the hydrogen, then the oxygen. And I have final say on what your grades look like. So what I'm really looking for is to make sure that you guys correctly understand what balancing an equation means. Because this is my first interpretation of understanding that you guys even know what that means. Because you guys have just been playing in your laptops from home, events, etc. Because unfortunately you haven't had the exposure to lab that you might have otherwise. Lastly, before I touch again upon balancing equations and the math, because I know that was a confusing section, I will touch upon the last questions here, 8, 9, and 10, because they're all essentially the same. They're all about identifying proper Newman projections. Now, unfortunately, I don't have a model kit with me to demonstrate proper Newman projection orientation. However, I will say, when something says look down upon the 3 to 4, what you need to do, ladies and gentlemen, in order to look at a Newman projection, picture the quad or the triangle here that you guys see as one carbon, and then the circle in the background as another carbon, okay? So, for instance, marker, perfect, I have one right here. Alrighty, so I'm holding up my board as such. Oh, you guys can't see anything, so it really doesn't matter. Great. Alrighty, doesn't matter. I will pull up Chemdro, and that's just fine. So in the meantime, Newman projection measures carbons the same way you would expect them to, except it measures, when it says down 3 to 4, it means the 3 is the dot in the middle of that tri-intersection, and the 4 is the circle, okay? I've actually never drawn Newman projections here before, but I will try briefly just for you guys. Or actually not at all, and I'll just explain because that'll be better, to be honest. Alrighty, so here we have, let me actually just draw exactly what you guys need to look at. 1, 2, 3, 4, 5. Here we have 2-methylpentane, perfect. Alrighty, and now let's pretend we're looking down the 3 to 4. So we're gonna count 1, 2, 3, 4, 5. So if we're looking down 3 to 4, we're looking down here to here. So here is one point, and here's another. So let's label them, even though these aren't the actual atoms, I'm just labeling them with random letters just to give them variables. Here's your 3, here's your 4, okay, understand, good, excellent. We know that since they're both carbons, this is just an example, remember these letters mean nothing, they're just variables. Since we know they're both carbons, this has 2 more hydrogens, and so does this. So we are able to add hydrogen, 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 hydrogen. And now look, we have 1, 2 points that we're looking down 3 to 4, which now have each, besides the conjoining point that combines them both, 3 points each. Now, if we look back to our Fisher projections, the circle in the back, all right, it has 1, 2, and look at my mouse, 3, and then the point in the middle, look at my mouse, 1, look at my mouse again, 2, look at my mouse one more time, 3. So the 3 points sticking out of the circle represent the carbon in the middle, which is closer to you. The 3 points stemming out from the circle, follow my mouse, giving you a second to follow my mouse. The 3 points stemming from the circle itself are each combined to 1 carbon. So we're assuming that this 1 point in the middle is 1 carbon, the one closer to you, and the circle, the entire circle, the entire thing is 1 other carbon connected to it, facing away from you, all right, going into that dimension, the Z dimension, all right? That's the best way I can explain to look at it. I will give you another example using my own personal molecular kit to try and describe this next week or in a couple of days. But in the meantime, this is all I can offer, unfortunately. There are 3 questions at the end that pertain to this. I will tell you that gauche, all right, gauche typically represents a 60-degree angle, meaning something that looks something like here, or even here, depending on the molecule you're in question, what the answer is, the circumstance for the question. And an eclipsed has these little things. So it's supposed to technically be overlapping, but if something was overlapping in this diagram, that where my mouse is, if you can follow, then we wouldn't be able to read it properly, would we? Because it's a line over a line. It was a line over a line, to our perception, 1 line. We can't perceive that. So we have a line eclipsed with another line, and we have it at a slight angle so that we can read it. And then here we have it requests for you to give an anti-description, all right, of the molecule down 2 different atoms. So that just means the molecule with the highest electronegativity opposite the molecule of the other highest electronegativity at the other end of the 2-bond atom that we atomic share that we give you for this question. So if it says look down C3 to C4 bond, you're going to look at the groups coming off of C3 and the groups coming off of C4, establish which ones are the most electronegative, and then anti them, and that's the most stable projection. But for the other questions, gauche, 60 degrees, that's one answer, and then eclipsed, right over each other, aka at a slight weirdly looking angle in the circle, because we can't draw eclipse in any other fashion. I really hope that this helped all of you with your questions pertaining to this lab assignment. I worked quite hard on it, and hopefully you all do extraordinarily well. So essentially, just to reiterate, I know it's been a minute, or more than a minute. It's a great deal of time. I know it's obnoxious, but stay with me, guys. Steam distillation, you are isolating one product using water as your mobile phase. All right. Simple distillation, you're isolating at least 2 products with boiling point difference of 40 degrees Celsius. Fractional distillation, you are separating at least 2, maybe more products of differing boiling points greater than 40 degrees Celsius. And it's strictly because you are using the column vane, because an inclined plane around a vertical axle gives you different pressures and temperatures at different quantized stages, meaning not continuous, but quantized, leveled. Another word for quantized is leveled. Stages at which you can determine its standard temperature and pressure for its boiling point, which is isolatable, which allows you to isolate it at different temperatures and pressure. If you guys have more questions for the calculations, let me know. The calculations are fairly easy, and all of them are included sufficiently in your lab manuals and notebooks. And I have Zoom time for office hours. So please let me know if you need any additional help and if I can help. I hope this was a great deal of help and aid to each of you, and Godspeed.